Hello everybody and welcome to the second video series for Chapter 8. We're going to study Lewis structures. If you look at the following chart, the Roman numerals are the group numbers from the periodic table, and beneath them is the outer electronic structure, or the electron configuration for the outermost energy level of the elements in the second period of the periodic table. What pattern do you see? The group number tells you the number of outer electrons. These are the valence electrons. It's important for you to notice that in the S&P, the first group has one outer electron, the second group has two, the three has three, all the way down to the noble gases, which have 8 and are stable. One way to show these valence electrons is by a dot diagram. If you look at the element, this has one dot, which represents its one outer electron, two dots for two outer electrons. What's important for you to notice is that they are single first, going around the element, and then they start doubling up. What pattern do you see here? That the group number becomes the number of dots that you put around the element symbol. This pattern works for all the periods in the S&P block. Sodium is in the first group, so it has one dot, where magnesium's in the second, it has two dots, all the way down to argon. You can use these dot diagrams to show how atoms bond together. When you do this, you are using Lewis diagrams or Lewis structures. Here's an example: lithium bonding with fluorine, beryllium bonding with two fluorines, and oxygen bonding with two lithiums. To show how the electrons bond together, you pair each atom's single electrons. We are next going to use the Lewis dot symbols for the main group elements to represent the bonding and structure for various species, molecules, compounds, and polyatomic ions. Some things you need to keep in mind is that all valence electrons from every atom will be included. All shared pair of electrons will be indicated by a dash. All unshared pair of electrons will be indicated by a dot. We will use the octet rule for guiding our principle. Let's look at a diatomic element first, which is H2Cl2N2O2. H2, each hydrogen, since hydrogen is in the first group, has one dot around it. What these two electrons will do is they will come together and be shared between the hydrogen. So hydrogen is sharing these two electrons between the both of them. That ends up turning into a dash. So with hydrogen, it will have one bond between it. The same thing will occur with chlorine. Each chlorine has a single electron. The other ones are all shared and paired together. What ends up happening is the two electrons between both chlorines will come together and be shared to form a bond. If you take a look, once the bond's made, you can see that this chlorine has 2, 4, 6, and then the share paired makes 8 for the blue chlorine. And on the red chlorine, you have 2, 4, 6, 8 electrons for the red chlorine. So using a shared pair of electrons between the two makes both chlorines have a stable octet, has 8 electrons around it. Looking at nitrogen, what ends up happening is nitrogen will share one set, then it will share two sets, but there's still no octet after sharing two. So here you have 2, 4, 5, 2, 4, 5, not enough. The third single electron will be shared between nitrogen, and if you take a look at the red, 2, 4, 6, 8, and the blue has 2, 4, 6, 8. What ends up happening here is because 3 of them are shared, nitrogen ends up having a triple bond between it. Oxygen has 2 sets of shared electrons on each oxygen and 2 single. So they'll share one pair of electrons, but if you count 2, 4, 6, 7, each only has 7 around it. They must share the last set of single electrons. 2, 4, 6, 8, 2, 4, 6, 8. They both have an octet around them. This is the correct Lewis structure for O2, a double bond. But really, oxygen acts like this where it has 2, 4, 6, 7 around it. But this will require a whole new bonding theory to explain it, and we'll talk about that in the next unit. Here are some rules for drawing Lewis diagrams or Lewis structures. You're going to decide which atoms are bonded, and you're going to count all valence electrons. Place 2 electrons in each bond. Complete the octets of the atoms attached to the central atom by adding electrons in pairs. Place any remaining electrons on the central atom in pairs. And then finally, if the central atom does not have an octet, you're going to form double bonds or triple bonds. The first step is to decide which atoms are bonded. So you're going to decide on the arrangement of atoms. For most formulas, the element written first is the molecule or ion that is the central atom, and then the remainder of the atoms are grouped around it. It's important for us to realize that the least electronegative atom is usually the central atom. If it's carbon, if carbon's in there, that's usually central. Hydrogen is a problem in oxaloacids where it is written first in the formula. However, we ignore hydrogen, start with the next atom in the formula, and place the H or H's on the O or O's. So when you have something like sulfuric acid, this H is not the central. Each hydrogen can only have one bond. So this would be your central, and then your hydrogens would be based off of 2 of the O's. You're going to count all the valence electrons, so you add up all available valence electrons. If the species is a cation, that is, if it is a positive ion, you're going to subtract positive charge from the total. If the species is an anion or a negative ion, then you're going to add a negative charge to the total. Now remember, these are electrons, so if it's a positive charge, you've lost an electron. If it's a negative charge, you've gained an extra electron. Divide the total by 2 to determine available number of electron pairs. Place each electron in a bond. Place a pair of electrons between each pair of bonded atoms to represent a single bond. You can either use a pair of dots or a dash. So here, if we're looking to write the Lewis structure for ammonia, the first letter is the central. Place all the other ones around it, step 1. Then you are going to, in step 2, each nitrogen has 5, and each hydrogen has 1. So 5 total electrons from the nitrogens, 3 total from the 3 hydrogens. That's a total of 8 valence electrons. If you divide by 2, that tells you has 4 electron pairs. So divide by 2, 4 electron pairs. Step 3, you're going to place a bond here, a bond here, and a bond here between nitrogen and each of the hydrogens. The fourth step is to complete the octets of the atoms attached to the central atom by adding electrons in pairs. So you're going to place any leftover electron pairs around terminal atoms to achieve their octet. These are the outer atoms. So the outer atoms are most electronegative. Do central atoms last. So go around and put any leftover electron pairs around the outside atoms. And if you have any left over, you place them on the central. If the central atom does not have an octet, then you need to start forming double bonds between the central atom and the outer element. Examine central atoms to determine if a double or triple bond is required to achieve the central atom's octet. Do so using unshared pairs if the central atom is carbon, nitrogen, phosphorus, oxygen, or sulfur. We'll go back to our ammonia example now to finish out step 5 and 6. On step 5, it says to place any leftover paired electrons on the central atom. Hydrogens can only have 2, only 2 electrons, because their electron configurations are 1s. 1 and s's can only hold a maximum of 2, so they are already filled. Nitrogen needs the last 2. If you take a look, hydrogen over here is a duet, which is 2 electrons. So 2 electrons only. And then nitrogen has 8. So it's stable. We don't need a step 6 because everything is stable in it. We don't need to do triple or double bonds. So there is our 1 through 6, our rules for drawing Lewis structures. Writing Lewis structures for ionic compounds is even easier since each atom gains or loses electrons to reach its nearest noble gas configuration. All you have to do is locate each element in the periodic table and determine the number of electrons it must gain or lose. So here's a few examples. Sodium is Na, and it will have 1 dot. Chlorine, Cl, has 7. So here you'll notice that sodium has 1 to give up. Chlorine could lose 7, but it's going to take a lot of energy to lose all 7. It's easier for chlorine to gain 1 electron. So what we're going to see here is Na is going to give its 1 electron to chlorine. And when sodium loses its electron, put the bracket here, it becomes a positive and chlorine becomes a minus. So how we're going to write this is we're going to write our Na plus, and then our anion we're going to write in brackets, place our valence electrons, and write a minus. This is very similar to what we did last year. Here we have lithium. It has 1 dot. Oxygen has 1, 2, 3, 4, 5, 6 dots around it. So oxygen has 2 single electrons that need to be bonded. So 1 lithium will give its electron to oxygen, but oxygen still has an available single electron, so we must have another lithium that comes in and bonds it. So the compound with lithium and oxygen, if you wrote it out, lithium is a +1, oxygen is a -2. If you drop and swap these, we get a lithium 2 and an O. So here we see why we need 2 lithiums. So we'll write this lithium, and then we're going to put the anion in the center because it's given an electron here. Fill in the valence electrons. This one gives an electron here. And each lithium is now a plus, and the oxygen is a -2 because it took on 2 electrons. All right, and then we'll finish up with potassium and sulfur. Potassium will give sulfur 1, so we must need another 1 here. So potassium each potassium is positive, and the sulfur is a -2 again. So Lewis structures for ionic compounds are a little easier because you're just looking at what electrons are available to be transferred between the 2 elements. What's really important is making sure that you use the correct notation with brackets and that you put the charges along with those. This picture here is from your book, and it does show you how lithium's 1s outer valence is transferred over to fluorine's 2p orbital, and lithium then becomes a positive and fluorine becomes a minus. So we would write this lithium plus, and they're showing you with a different color. They're showing you here that different color is the electron from lithium. There are some exceptions to the octet rule. Odd electron molecules, things like NO and NO2, they will have an odd number of electrons. So you may see 1 single electron on a central atom here. They're just exceptions. Incomplete octets, we have hydrogen, helium, beryllium. The reason that these are incomplete is because their electron configurations are 1s's. So the most that they can fill in is 2 electrons there. And then you'll have expanded octets. Phosphorus and sulfur are usually very expanded in what they're able to bond with. Phosphorus, for some reason, and we'll talk about it in chapter 9, phosphorus can typically make 5 bonds, and sulfur over here typically will make 6 bonds. So if you see a 5 bond or a 6 bond in a molecule, it is because it's an exception to that stable 8 electrons in the outer energy level. All right, that ends our lecture on Lewis structures. The next lecture we're going to talk about formal charges.